Since the 1960s, carbon emissions from fossil fuels have increased from 11 billion tons per year to almost 37 billion tons today. Our planet has also become 1 degree Celsius warmer since the start of the last century and is expected to warm by a further 1.1 degrees to 5.4 degrees Celsius by the year 2100. While these numbers may seem small, their repercussions are not. Sea levels have risen as melting glaciers and ice sheets add water to the ocean, and we're being hit by ever more frequent and severe heat waves, droughts, floods, and storms. Natural disasters, many driven by climate change, caused global economic losses of $313 billion in 2022 alone. As a result of these changes, climate change has been at the top of policy agendas for decades, and a lot of money has been poured into renewable energy technologies and EVs to help us move away from fossil fuels. Solar and wind drove a 700 terawatt-hour increase in worldwide renewable power output in 2022, while the market share of EVs rose from 4 to 14% from 2020 to 2022 and is expected to keep rising further. But all of this might not be enough, since renewable energy continues to be limited by intermittency, while EVs continue to be powered by electricity that still usually comes from unsustainable sources.
If emissions aren't reduced, what next?
Enter artificial cooling, an audacious solution that harnesses the power of technology to tackle the heat head-on. So what is artificial cooling, more seriously known as geoengineering? What does it have to do with disastrous volcanic eruptions? And could it spell an end to all our climate change-related woes? Before we proceed, if you haven't already subscribed to our channel, could I please request that you do so? We're a team that's working really hard to bring you these videos, and we need to reach 1,000 subscribers so YouTube will allow us to monetize our channel. Your support means everything to us, even if it's free. Now, without further ado, let's dive in. In 1982, the El Chichon volcano in Mexico erupted in a series of 3 explosive outbursts, resulting in the loss of thousands of lives and causing significant displacement. But this eruption did more than just cause immediate devastation. Surprisingly, it also had a direct impact on the Earth's climate, and the average temperature fell by 0.4 degrees Celsius in the northern hemisphere. This happened because the explosion associated with the eruption had pumped sulfur dioxide and aerosols into the stratosphere that spread, forming a barrier that blocked incoming solar radiation.
It was so powerful, it produced a gas cloud that reached the stratosphere. The explosion caused a lot of damage locally, but the cloud itself did something extraordinary.
In 1991, another volcanic eruption had the same effect. The Pinatubo Mountain in the Philippines exploded. As a result of this eruption, by 1992, Earth's surface temperature had dropped by 0.5 degrees Celsius and took 3 years to rise back to where it had been before the volcano had erupted. The eruption of these volcanoes gave birth to the idea of geoengineering, or artificial cooling, an intentional large-scale modification of Earth's natural systems to combat climate change. Many theoretical techniques could be employed to achieve this, and in the remainder of this video, we're going to look into a few. One approach is known as solar radiation management, or SRM, and is built upon a simple principle known as the albedo effect, which is basically the idea that bright surfaces reflect more light. Many strategies fall within the umbrella of SRM. One involves ocean foaming, which is simply the creation and distribution of bubbles in the ocean, since these reflect 10 times more sunlight than regular seawater. Some research suggests that introducing bubble across merely 5.5% of the world's oceans could cause global temperatures to fall by 5.5% by 2069. Another strategy involves injecting aerosols into the stratosphere to replicate the impact of the volcanic eruptions discussed earlier. Aerosols like sulfur can merge with water in the atmosphere to create a sunlight-reflecting barrier. Projections suggest that by investing $2.25 billion annually on this activity, we could bring down global temperatures by 0.3 degrees Celsius, which sounds absolutely worth it, given that climate change-related disasters cost just the US $165 billion in 2022 alone. A third strategy is a localized approach that involves increasing how much sunlight is reflected back into the atmosphere by altering our farming and construction practices. One simple solution involves painting our rooftops with reflective paint, and this has already been successfully tested with the New York Roof Program, which launched in 2009 and covered over 5.7 million square feet. But SRM is not the only method on the table. We could also try to directly remove excess greenhouse gases from the atmosphere, and multiple techniques could once again be deployed to make this actionable. One such technique involves the use of biochar. Biochar is a type of charcoal that is created by pyrolysis, a process that involves heating biomass in the absence of oxygen. This process locks carbon into the biochar, which can then be applied to soil, where it can help to improve soil quality, increase crop yields, and reduce greenhouse gas emissions by absorbing carbon dioxide directly from the atmosphere and reducing nitrous oxide emissions from soil. While on the plus side, biochar is a relatively cost-effective way to reduce greenhouse gases, the process of creating it can ironically actually release these gases into the atmosphere. In addition, its effectiveness as a greenhouse gas warrior is still also under hot discussion. Enhanced weathering is another technique that aims to remove CO2 from the atmosphere. It involves burying silicate rock particles in soil, where they react with water and carbon dioxide, forming bicarbonate ions that help dissolve additional CO2 from the air. This approach, however, requires extremely large quantities of rock particles in the order of about 2 tons to remove a single ton of CO2. Direct air capture is yet another technique that aims to extract carbon dioxide directly from the air and store it for future use, such as in the production of carbonated beverages. 18 direct air capture plants are currently in operation, but most are still little more than experiments. While geoengineering certainly sounds promising, is it in fact too good to be true? Let's for instance consider SRM. While on the one hand, it could mean fewer winter storms and hurricanes, on the other hand, SRM-based techniques could also weaken the summer winds that help clear air pollution and potentially reshape our climate in ways that we can't anticipate. The aerosol injection method has its drawbacks too. While it may cool the planet, it fails to tackle other greenhouse gas concerns like diminished rainfall. The alteration in atmospheric composition that it causes could affect photosynthesis, a critical process for life on Earth, and it could also change the composition of the atmosphere, robbing us of our iconic blue skies. Even carbon dioxide removal techniques face obstacles. Enhanced weathering, for example, could disrupt soil nutrient composition and harm crops, while the high energy demands associated with direct air capture might not make it the most practical choice in our current energy climate. Critics also warn that geoengineering could become a smokescreen, enabling corporate lobbyists, climate change deniers, and some governments to stall on carbon legislation and skirt green energy investments. So where does that leave us? Have we stumbled upon the ultimate solution to all our climate woes? Maybe, but maybe not. Geoengineering still remains a complex and hotly contested field with ethical dilemmas, governance issues, and consequences that are simply impossible to predict. Nevertheless, this doesn't mean that we should halt research. Our continued efforts could still arm us with a more direct weapon in our battle against climate change.
In the end, the risk of not doing research on this may be bigger than the risk of doing research.
So what are your thoughts on artificial cooling and the potential that it holds? Let us know in the comments below. Don't forget to hit like and subscribe, and I'll see you again in the next video.